All right, yes, students, we're going to get started on what is going to be the last virtual lesson for the 2010-2011 school year. The topic being presented this afternoon is rate functions. As the name implies, we're going to be looking at problems. We're going to be looking at functions that are communicating rate information. So lots of problems fall into this category of rate functions. Physics problems are examples of rate functions. You look at velocity. Velocity is a rate. It's a measure of how your position changes over time. We look at containers filling up. They're filling up with water. The water is entering the container. The units are gallons per hour, or maybe it's cubic feet per minute. Right? All of these rate functions we're going to apply some calculus to. Sometimes it'll be derivative calculus. Sometimes it'll be on the other side of the house. It'll be integral calculus. The two problems I'm going to present this afternoon, there's one that focuses mostly on derivatives, and the other one is going to focus mostly on integrals. So as we've done in previous videos before, looking at how these have been assessed on past AP exams, let's look at some of the background knowledge that we're going to need in order to be successful. Okay, so one of the really important things that we're going to have to pay particular attention to with these rate functions is going to be our use of units. And if you do this right, you can actually use the units to help you through the problem, to help give you some advice as to, do I want to take a derivative, do I want to take an integral? Paying attention to the units is going to be really helpful. Also, your ability to communicate your final answer with the appropriate units is huge. We've talked about this all throughout the course, that AP folks will award points, usually 1 point within each free response question, for the proper use of units. That also means if you're not using the units appropriately, that you stand to lose that point. And that is a horrible thing to do. So let's be really careful. If, for example, we're in a geometry problem and you have taken a derivative, right, and you wind up with an answer at the end that says dv dt is equal to negative 0.925 cubic meters per second. Well, first of all, if I'm asked to communicate this in a sentence, I'm not just going to write dv dt equals negative 0.925 cubic meters per second. V might be volume if we're in a geometry problem. And I would have to interpret this as how my volume is changing, so dV, like our delta V, how volume is changing over time. So in this problem, with this made-up problem, we would want to communicate that the volume of our object, whatever it might be, is changing. Now, how is it changing? Because this rate is negative, the volume is decreasing at a rate of 0.925 cubic meters per second. Definitely want to pay careful attention to the negative. That means that your rate is decreasing. You want to keep in mind the context of the problem. If V is volume, you'll want to mention that. If we're looking at a population problem, maybe I have dp dt, and this might be number of people. So dp dt is 812 people per year. In a population problem, I would probably want to communicate that my population is changing. Well, how is it changing? My population is growing, because 812 is a positive number here. It's growing at a rate of 812 people per year. So definitely want to make sure that we're paying careful attention to the units. Like I said, they're going to be really helpful. Another thing that's going to come up in these rate functions is our ability to use the chain rule. With my students at Southwest, we talk about the baby and the mama. The chain rule, if you have a function that has a function inside of it, so the example I have over here is that I have some function y, which is defined by a function plugged into f. So this is f of g of x. The way that we would take the derivative, we call f the mama, because that's the big function. We call g the baby. So the derivative using the chain rule is you take the derivative of the mama, so f prime, and you leave the baby alone. So f prime evaluated at g times the derivative of g prime. Maybe your calculus teacher doesn't talk about the derivative of the mama with the baby left alone times the derivative of the baby, but the essence of the chain rule is the same. You take the derivative of the outside function in whatever way you do, you leave the inside function alone, and then you multiply by the derivative of the inside function. So let's look at this example. I've got y is equal to the cosine of x squared plus 1. In this way, the outside function is the cosine. The inside function is this x squared plus 1. Well, what do we know? We know that the derivative of the cosine is negative sine. I'm going to leave the inside function alone. So this was the derivative of the mama. Derivative of the cosine is negative sine. Leave the baby alone. We're not done yet because now you need to go back and take the derivative of the baby. Since x squared plus 1 is the baby, the derivative of x squared plus 1 is 2x. You can leave the answer like that. You could also simplify the answer to negative 2x sine x squared plus 1. Let's look at another example. Now we have cosine squared of x plus 1. Well, this one's going to be a little bit trickier. We're actually going to do two chain rules. Let's look at this one. I'm going to first rewrite this. Cosine squared, what we learned back in pre-calculus, means that we are taking the cosine and we're going to square the entire result. So in this case, I have the cosine of x plus 1 being raised to a power. So if I cover up cosine x plus 1, I do have a function that we know well. It's something squared. Well, how do I take the derivative of something squared? Our rule is we bring the 2 down in front, so it's 2 times that something, 2 times the cosine of x plus 1, to the 1 less power. Now, because it's a chain rule, I have to go back and I have to take the derivative of what's on the inside. Well, what's on the inside is cosine of x plus 1. In order to take the derivative of the cosine of x plus 1, I have to take the derivative of the cosine, which is negative sine x plus 1. Now, since I have this x plus 1, I'm going to have to multiply by its derivative, which is 1. I can simplify that if I would like to get y prime is equal to negative 2 sine x plus 1 times the cosine of x plus 1. These are not necessarily problems that we're going to see specifically in these upcoming AP problems, but I definitely wanted to set the stage, make sure we're clear with the chain rule. Chain rule works really well when you have a function hidden inside of another function. This is pretty standard in all of our AP calculus classes. These are standard questions that you're going to see on the AP exam. You might want to pay particular attention to the second one because we had a chain rule within a chain rule. But before we actually move any further, there is another version of the chain rule that probably has not received a lot of attention this year. I know I haven't given it nearly as much attention as I need to, and it is definitely going to show up on one of the AP problems. So let's look at this other version of the chain rule before we move on. The last big idea from calculus that I want to make sure that we touch on before we launch into the problems is our friend the fundamental theorem of calculus. It has to be in your toolbox. This is something that is going to be assessed quite regularly on the AP exam. It's going to be especially helpful if you have been given information about the derivative and you've been given a starting value and you need to know the value of a function at another point. At this point in the course, this should be something that you're seeing on a regular basis. And for me, when we're doing these rate functions, whenever I'm given information about the derivative, but what I need is information about the original function, this is going to be what is on my list of ideas to try. And you can use this as long as the original function is continuous, as long as you know a starting value for the function. And I think that should do it. Onward to Part A. In Part A, the specific question is, how many cubic feet of snow have accumulated on the driveway by 6 a.m.? Keywords I want to pay attention to. This word accumulated, how much snow has been added onto the driveway. In calculus, we do accumulation using the integral. We want to know by 6 a.m. Since it started snowing at midnight and it is now snowed for 6 hours, when we're looking at our integral, we're going to look at an integral from 0 to 6. Now we need to make a decision, which function are we integrating? We have g, which represents the rate that she is taking snow off of the driveway. We have f, which is our rate function, being measured in cubic feet per hour, and that tells us how quickly the snow is piling up on the driveway. Since that's what they're asking us in part A, we are going to integrate f of t, which is the 7t e to the cosine of t power. We're going to integrate this with respect to time. We're going to start at t equals 0, which is midnight. We're going to end at t equals 6 because the question wants to know how much is piled up on the driveway by 6 a.m. Since this is a calculator active question, I am just going to write down my initial integral. I'm going to type that into my calculator, and when I do that, what I'm coming out with is 142.274. Now let's pay attention to the units. This over here was f of t was being measured in cubic feet per hour. My dt, we're talking about a change in time. That is going to be measured in hours. My unit of cubic feet per hour will cancel out with that hour over there, giving me a final answer of 142.274 cubic feet. That's how much is piled up on the driveway by 6 a.m. And that's it. That was part A. 2 points were awarded for this question. 1 point for the original integral setup. The second point was for your answer. Accurate to 3 decimal places, always with the proper units. If you don't have the cubic feet units, you're not going to earn the second point. So be careful. Okay. So we need to find the rate of change of the snow on the driveway at 8 a.m. In order to do this problem, we need to keep in mind what's going on in the situation. At 8 a.m., we still have snow falling onto the driveway. Now, the difference is, not only do we have snow falling onto the driveway at 8 a.m., but at 8 a.m., Janet is up, she is shoveling snow off the driveway, and we want to find out what's happening to the amount of snow on the driveway at that time. Well, that can be answered pretty easily. If we look at f of 8, f was the rate at which snow is piling up on the driveway. Let's figure out what that is at 8 a.m. We're going to also need to find the rate at which Janet is shoveling snow at 8 a.m. And we're going to subtract these two. Now, when I do that, in order to find f of 8, I'm going to evaluate this f of t function at 8 a.m. And the answer that I get from my calculator, again, very calculator active, 48.417032. The units there would be cubic feet per hour. Minus, how quickly is Janet shoveling snow off the driveway? Well, at 8 a.m., that means that I am between 7 and t equal to 9. She's shoveling at 108 cubic feet per hour. When I subtract those two, I'm going to get negative 58.2968. Again, always want to pay attention to the units. Since this was a rate function and the units were cubic feet per hour, and this is a rate function being measured in cubic feet per hour, then my final answer is going to be cubic feet per hour. Depending on how the question is worded, this answer might be sufficient. You might also need to write a sentence. And the sentence should go something like this. At 8 a.m., the amount of snow on the driveway is decreasing at a rate of 58.296 or 59.297, depending on rounding or truncating, cubic feet per hour. One last time in one continuous sentence. At 8 a.m., the amount of snow on the driveway is decreasing at a rate of 58.296 cubic feet per hour. That is a perfect answer to Part B, and I believe 2 points were awarded here. It may have just been 1 point. This was a relatively straightforward question. All right, onward to part C. Part C, let H of t represent the total amount of snow, now in cubic feet, that Janet has removed from the driveway at time t hours after midnight. And then we want to express H as a piecewise defined function with domain 0 less than or equal to t less than or equal to 9. So this was definitely a new question for me when I saw it. I hadn't seen a question like this on the AP exam before. But let's take this one step at a time. H represents the total amount of snow that Janet has removed. They want us to look from 0 to 9. Well, let's think about this. At time 0 is midnight. How much has Janet removed from the driveway? She hasn't removed anything. In fact, 1 hour later, at 1 a.m., Janet is still sleeping. No snow has been removed. She doesn't start shoveling snow until 6 a.m., so this first part, 0 less than or equal to t less than 6, should be the easiest part of your piecewise function. And what we can say is that h of t, the amount that she has removed from the driveway, is going to be 0 if 0 is less than or equal to t less than 6. Look at that. It took us about 5 seconds, and we've already figured out part of this piecewise function. We've got the first 6 hours covered. Now we need to look at this next 1 hour interval. So from 6 a.m. to 7 a.m., she is shoveling snow at a rate of 125 cubic feet per hour. So for any time in there, 6 less than or equal to t less than 7, if I want to find out how much has she removed, well, what am I going to do? I'm going to take the integral from 0 to whatever value it is of g of t dt. Now, since we're on the time interval 6 to 7, what we know is that t must be bigger than 6, or I guess it could be equal to 6. So we're going to break this into two integrals. How much she shoveled from 0 to 6 a.m. plus how much she has shoveled from 6 to that final value of t, g of t dt. We've already answered this part. How much has she shoveled between midnight and 6 a.m.? She hasn't shoveled anything at all. She is in bed sleeping. Now we need to figure out how much has she shoveled from 6 to some stopping point t. Well, if we are between 6 a.m. and sometime before 7 a.m., we know g is defined to be 125. So we're going to get the integral from 6 to t of 125 dt. The integral of 125 with respect to t is going to be 125t. We go from 6 to t. We evaluate our antiderivative at the upper limit minus evaluate the integral at the bottom limit. What we're going to get is 125 times t minus 125 times 6. We're done. Don't simplify it unless you want to. If you do choose to simplify it, it will be 125t minus 750. And that is true on the time interval 6 less than or equal to t less than 7. So if we want to know how much has been removed at 6:30, we'd be able to use our new piecewise defined function. 6:30, t would be 6.5. I would plug it in here. I would be done. Happy day. Now let's look on the next interval in question, between 7 a.m. and 9 a.m. We know she's slowed down a little bit. So if we are looking from 7 a.m. to 9 a.m., inclusive of the 9 a.m., well, h of t is going to be how much did she shovel from midnight to 6. Again, we know the answer. She didn't shovel anything at all. She was sleeping. Plus, because now we're between 7 a.m. and 9 a.m., how much did she shovel between 6 a.m. and 7 a.m.? It was a rate of 125 cubic feet per hour. We'll integrate that with respect to t. Plus, how much does she shovel between 7 a.m. and whatever value of t we choose to stop at? Her rate there is 108. We integrate that with respect to t. The integral over here we know is 0. The integral of 125, well, 125 is a constant, nice horizontal line, from 6 to 7. That is going to be 125 cubic feet of snow removed, plus this next one, 108 times t minus 108 times 7. Again, simplify that if you want to. Don't simplify it if you don't want to. That is fine. This will simplify if you want to down to 108t, 125 minus 108 times 7. What is that going to be? That's going to be 108t minus 631. And that's going to conclude that one right there. There it is. That is our piecewise function. She removes 0 feet of snow between 0 and 6 a.m. Between 6 a.m. and 7 a.m. at any time in that interval, if I want to know how much has been removed since she started shoveling at midnight, it's going to be 125t minus 750. If I want to know how much snow she's removed for some time t between 7 a.m. and 9 a.m., it'll be 108t minus 631. That is part C. On to part D.